Yeah, thanks for being here for this talk. I know there's like a very interesting workshop at the same time going on. But I hope this will be like a little bit exciting as well, although it's more on the academic side, the talk. I will speak about evolution of a side channel, and this is about the static power side channel, which is like a main topic of my PhD thesis. And the talk will like outline the whole story through my PhD thesis with like the final result, which until then I never really had the time to publish, because at some point I had the degree, and then like the motivation to do this final paper was a bit lacking. And now I finally had the time and can present it here. I have to start with something boring, so acknowledgements. Most of the work has been accomplished during my PhD at University Bochum. Right now I'm doing my postdoc at UC Leuven in Leuven-la-Neuve in Belgium, and I did it under supervision of Amir Moradi. And the project has been funded by the German Research Foundation under this NASA project, Nanoscale Side Channel Analysis, Physical Security for Next Generation CMOS ICs, which was a very interesting project. And I had like the pleasure to work on it completely alone, which gave me like a lot of freedom and money to explore like the things that I was interested in. And in the later parts of the project, this excellence cluster in Bochum called CASA also funded it. Okay, let's get to the introduction. I guess you all know that energy consumption in computing hardware is one of these factors that we can use for side channel attacks if we have physical access to a device. And digital integrated circuits are typically modeled as state machines, where state transitions are triggered by events such as the clock signal, clock edge. And whenever one of these state transitions occurs, energy is consumed because electric charges in the device are moved, which also creates an electromagnetic field. And these things, the power consumption and the electromagnetic field, they are usually used for performing power side channel or EM side channel attacks on cryptography. How does it look like on the transistor level? So here we have the simplest CMOS gates, namely a CMOS inverter, which is built from a PMOS transistor at the top as pull-up network and a NMOS transistor at the bottom as pull-down network. And if we have an input transition, which goes from high voltage to low voltage, the upper transistor turns on, the lower transistor turns off, so the output capacitance is charged. And the output level goes high, the voltage level at the output goes high. Analogously, the opposite transition at the input causes the opposite transition at the output, because the output capacitance is discharged as it's pulled to the ground. Then we have, because all of this doesn't happen instantaneously, we have this intermediate voltage where both transistors are technically on a little bit, and where a short circuit current flows between VDD and ground. This also causes power consumption, but it's a less cause of side channel leakage, I would say. Now the question is that all? So is energy only consumed if state transitions or, let's say, active computation occurs? And the answer is no. We would like that to happen, but the reality is different. Namely, we have these leakage currents in CMOS gates. That is depicted here. So an off transistor is not completely off. It's not a switch, like a light switch that doesn't conduct anymore, but it conducts a little bit. So we have these subthreshold currents, because with current voltage levels in ICs, we cannot get beyond that. Physics tells us that. We always have the subthreshold current, because if I'm below the threshold voltage, the conductance doesn't go to zero immediately. We have some drop-off, which happens, and I can only decrease the voltage so much. So I still have this both in NMOS and in PMOS transistors. I also have the junction leakage for the PN junction. And I have gate oxide leakage currents everywhere, essentially where there is a potential across the gate. Now, why are these leakage currents interesting? They are mostly a concern in VLSI circles, because that's annoying. Your device, even in idle or standby, consumes quite a lot of energy. The development of these leakage current actually depends on like the feature size of the technology. So newer technologies generally have higher leakage currents. The dynamic power, on the other hand, it decreases per unit but because we put more units on chips these days, the total one also increases, but not as much as subthreshold and junction leakage shown here. This figure has been used like many times in many publications. It's based on a prediction from 2003 and has never really been updated. So I wouldn't put like my hand into the fire for this to be completely true, but we will see that we arrive at similar conclusions. Now, what I can observe with leakage currents of CMOS logic gates is that I have a data dependency. So here you see the SPICE simulated leakage current of a 2-input NAND gate in 22 nanometer technology. I pulled that from a paper which apparently was allowed to publish that stuff. And we have a NAND gate, inputs A and B, and depending on the values of A and B, we have very different leakage currents of those gates, right? Which tells you whenever I have like logical values at the inputs of logic gates and they are static and stable, I can learn from the leakage current about what is going on, which type of data is processed. Why does that happen? So here we have like the transistor level description schematic of a NAND gate on the left side. And for different A and B values, we just remove the on transistors in this figure and only leave the off transistors, which are the leaking ones, right? Because we always have an off transistor between VDD and ground. That's how CMOS is built. And obviously in the case of A0, B0, we have two NMOS in series, which are between VDD and ground, which conducts much less current than two PMOS in parallel as we have for A equals 1 and B equals 1. And even like the cases A1, B0 and B1, A0 can be distinguished quite well because the lower NMOS transistor is then pulled up by another NMOS transistor, and NMOS transistors are not good at pulling up, so it doesn't pull up to VDD completely. To summarize that a bit, so the static power consumption of CMOS chips silently leaks about the internally stored values. So that means even values which are just stored in flip-flops and are input to some logic gates and are not even currently processed, so the device can be completely idle, they are leaked. And if I have this as a stable state and I can measure that for some time, then I also get like very low noise measurements because it's a static effect that I sample. I don't have to rely on this instantaneous description of a transistor switching that I use, but I have a stable effect so I can get quite low noise measurements. Also, what we know from physics is that I can use the voltage and the temperature to really control these leakage currents. So voltage and temperature increase, both really ramps up these leakage currents. So if I want as an adversary, I can really fry my chips in like a climate chamber and ramp up the voltage, and it leaks much, much more. And finally, what we also know, as you have seen in the figure before, the leakage currents are known to increase significantly as the feature size of transistor decreases. So this is actually a side channel that becomes more dangerous in newer technologies, which is definitely not what we want to have as like crypto designers would say. Next, I want to talk about the prototypes that we have developed. So this is like the digital IC prototyping timeline during my PhD. So I did like 6 different chips. In this talk, I will only talk about these 4 of them because they are all in progressively smaller CMOS feature sizes. I cannot tell you which foundry it is, but I guess it's not too hard to figure out. They have all been manufactured via Europractice IC services as mini ASICs, and it's from 90 nanometer over 65 nanometer, 40 nanometer to 28 nanometer, and these will be analyzed in the following to see how this static power side channel develops over multiple technology generations. Now here are some details about the chips that we have prototyped. So you can see like the 90 nanometer one is actually the largest in size. So although the figures are the same size, the chips are not the same size. So the 28 nanometer chip, the yellow one on the right side, it's roughly half as large as the one on the left side. And the standard cell area, which is like the dark bluish part in the middle of each chip, that also decreases in size from 90 nanometer on the left to 28 nanometer on the right. However, the most cells, the most standard cells, the most computing power is contained on the right, the smallest chip, because it's 28 nanometer technology. The cells are much denser and I have much more computing power on it. So this one has 1.5 million standard cells, while the 90 nanometer one has only 500,000. There's also the number of unique standard cell types, which only tells that also these standard cell libraries, they get much more complex in smaller technologies. Then the core voltage is important because we will play with it in the next slides. This goes from 1.2 volts for the two older technologies to 0.9 volt for the 28 nanometer chip. And the cost is given for like these Euro practice low cost MPW fabrication prices. If you want to do such a chip without funding from the European Union, it will cost you much more, so you can add a few zeros in this. Here are some chip pictures. So I just like to show chip pictures because I spent like quite some time of my life on developing these things. You have some naked dies on the left. You have a bonded die in the next to it. Then a package die in this JLCC 44 package. And this is how large it looks in reality. So the chip inside is only 2 times 2 millimeter, and this one is like, 1.5 centimeters. And then on the right side, it's like the packaged die on a PCB board. Here are some scanning electron microscope images from pre-processed chips on the backside. It's not really important for this talk, but I wanted to advertise a little bit that my colleagues Andres and Steffen are giving a talk about those same chips with scanning electron microscope images tomorrow. Here are the measurement boards that we developed. So we started with the one on the top left and ended up with the one on the top right. So they actually work with the same FPGA device that was used in the previous talk, this CMOS A7 of Vigilant. You can just plug it as a breadboard on this PCB, and then you can handle the chip. And what is very important is this separation between the left side, where you have this where you can plug this FPGA board, and the right side where the ASIC goes. So we really have completely separate power supplies of both types. And we have isolation of the I/O signals in the middle, so they go through these expensive isolation devices to have a completely discoupled power profile on both sides. Let's talk about the measurement setup, because, when I started this project, not many people had done practical experiments on this, so we had to build this from scratch. And it's a bit more difficult than doing dynamic power side channel analysis, because you have a very low amplitude of the signal, and your signal is also super susceptible to temperature and voltage variations. So if you want to keep that stable, you also need to keep those values really stable. Naturally, you can only target values like intermediate values, sensitive intermediate values, which are stable for some time. So either they are stable for some time by design, because you have a low frequency device, or you have an idling coprocessor, let's say, which has some loaded data but is not currently computing, or you have to force the device. If you have an external clock, for example, you just cut off the clock connection and stop it going. This last option, of course, also allows different effects like clock glitching and whatnot. In total, the time consumption per measurement is significantly higher. So you need milliseconds instead of, few microseconds that you would need for getting dynamic power trace. So this is the first setup that we came up with, the first complete one. On the left side, you have this climate chamber, which is there to completely control the temperature, keep it very stable. And we have put the device under test, the board, the amplifier inside of that. And we have a sealed hole where the cables go through. And the power supply and the oscilloscope is then on the outside. So we naturally started with a setup that was used for other side channel experiments. So we had good oscilloscope in the side channel lab, and wanted to build a setup based on that. And it's what we accomplished here. One of the ideas was that we have this low noise DC amplifier, which is also temperature resistant, directly on the board, so that we don't need to carry non-amplified signals over long cables in the setup, so that it's directly amplified and then transported. So there's a gain of 1000, low noise DC amplifier. Then we notice that we still have some high frequency noise in the measurements that arrive at the oscilloscope. That might be because of the climate chamber and its operation, or because of the remaining setup. So we built like a custom low pass filter with a cutoff frequency of 100 Hertz. And this is a sample trace without the low pass filter, so before we remove this high frequency noise. And what you see basically is the clock is on at the beginning, but no real computation takes place. And I'm starting a core. This is only a very tiny peak. And then I stop the clock, and then I ignore everything that happens in time period T1 because it's like still a bit influenced by this voltage drop. And then I take like all values in period T2 and average them to like a singular value that I take as my measurement trace. And then I switch the clock back on, continue the computation, and can do everything as before. Like I said, if you have a situation where you don't need to stop the clock because like the target values are there for a longer time period as well, then the running clock during measurements is no problem. We tested that. It has no effect whatsoever. Here we just do that to keep the intermediate value that we want to target stable artificially. And yeah, that's the same trace with the low-pass filter, so you can see that quite some noise has been removed. And this is what the setup with the oscilloscope looks like. So DC amplifier board, ASIC in the climate chamber, low-pass filter oscilloscope outside of the climate chamber. Yeah, so we worked with that and published a few papers with this setup as well. And later we figured out that we actually could have saved the time and just bought a device that is built for measuring pico or nanoampere strong currents. And we took like a Keithley source meter, and we get like basically the same quality of results as our dedicated measurement setup. Even though I have to transport these non-amplified signals through the long wires, but it works just as well. So if you want to pick up on that challenge, then don't use an oscilloscope, use a source meter or source measure unit right away. The climate chamber is still needed though to keep the temperature stable. Yeah, this is the schematic of that cell. Now what you need in both cases is a moving average filter with some adjustable window size. This is just, you will see that over time, so this is like many measurements. This is not one measurement. This is like many measurements plotted. Each of them is only a single value. And over time, you have some low frequency noise because even in the climate chamber, the temperature is not perfectly stable. And these small variations you still see going up and down. So you will need to remove that artificially by post-processing. Yeah. Then I'm presenting some results that we published at CHES 2019, I believe. There we did like the first comparison. At that point, we only had the 90 nanometer and the 65 nanometer chip. So we only compared these two, and we wanted to have some target at the very beginning that we know leaks a lot. So we took like a 1024 bits high fan-out input register. So it's like many cells that are leaking about that. And it has an average fan-out of 11. And I completely fill it with zeros or ones. So it's like either 11,000 cells leak about all zeros or they leak about all ones. And then we compare how it looks on both chips. And the result is plotted here on the top for the 90 nanometer ASIC, on the bottom for the 65 nanometer ASIC. Please note that the x-axis on the bottom row is 10 times as large. So the distributions are not more narrow. It's just the way of plotting here because it's 10 times as much. So the difference of means is actually much, much larger. And what we can see from left to right, so left is like room temperature where we assume 20 degrees Celsius. In the middle, we did that same thing at 90 degrees Celsius. You can see that in both cases, it widens the gap between the two distributions, so they are much better distinguishable. I mean, they are already perfectly distinguishable beforehand, but the difference increases. And if I additionally also increase the voltage from 1.2 to 1.6 volt, it helps in both cases too. Those results are summarized here. And And essentially what you can see is that the 65 nanometer chip is 10 times as susceptible to this kind of information extraction as the 90 nanometer chip, which prompted us to find out whether it's like the same when going further down for 40 nanometer, 28 nanometer, which is then what we have done here. So yeah, if you have been falling asleep already, this is the part to wake up. This is like the new results and the important part. So we have on all 4 chips like the same AES coprocessor, AES 128. It's synthesized from the completely identical RTL code, and then we have analyzed it on all 4 devices. And what you see in these histograms, distributions, is we measured once for a fixed value, then for another fixed value, and also for a random value, to see if I can distinguish these 3 cases. And for the fixed classes, I tried to take some which are outliers at the outside, right? And on the bottom, there is a correlation power analysis attack, which tries to isolate the correct key candidate from the incorrect key candidates using the Pearson's correlation coefficient with some power model, which in this case is some linear combination of the bits, so like Hamming weight or derivations of it. What you can see is that the 90 nanometer chip is basically not detectable, so visually you cannot really distinguish the distributions for the 3 cases. And yeah, I mean, the correct key candidate in black is kind of at the top, but I wouldn't call that a successful attack. Then for the 65 nanometer, 40 nanometer, and 28 nanometer, we get much more successful attacks. So this is the same setting. We have the same setup, we have the same measurement process, the same post-processing, everything is identical. And we get like much higher susceptibility the smaller your CMOS technology goes. Now, if we repeat the same thing for 90 nanometer technology, it's basically amplified, right? So here's the difference. In the 90 nanometer case, now the attack works. It's still not perfectly visually distinguishable. And for the other case, it's like the difference of means between the distributions definitely increased in all cases. So this is something that just makes attacks more powerful. You just have to grill your chip in a climate chamber at higher temperatures, and the attacks become more successful, which you cannot do for normal power side channel attacks. Then we did the same thing for increased temperature, so 90 degrees Celsius and 50% overvoltage. And then we get like very successful attacks in all cases, and like the relations become a bit mixed. But this comparison, I would say, is not perfectly fair, because if I increase like 1.2 volts by 50%, that's like 0.6 on top. If I increase like 0.9 volts, that's like by 50%, that's like 0.45 on top. So the gap is not, I mean, the gap is not constant, but the gap is relative to the supply voltage that the chip uses. And here are those results plotted. On the left side, it's the maximum correlation coefficient in the attacks. Then the blue bars are for 20 degrees Celsius, the orange graphs are for 90 degrees Celsius, and the yellow graphs are for 90 degrees Celsius and 50% overvoltage. And you can see, especially for like the 20 degrees Celsius, so like the normal operating conditions, there's like a more than linear increase from 90 nanometer to 28 nanometer in the correlation coefficient of the attack. And on the right side, we have like the number of traces for a successful attack plotted. And here the y-axis is in log scale. So here, the differences for the 20 degrees Celsius case, they actually show that for each of the technology steps, we gain 1 order of magnitude. So we have to have 1 order of magnitude less traces to attack this. So we have like exponentially decreasing security from like the 90 nanometer chip towards the 28 nanometer chip for the same kind of attack. For the other cases with 90 degrees and 90 degrees and 50% overvoltage, it's a bit mixed and washed up, but I want to highlight that we have like really gain an order of magnitudes for each technology generation for the 20 degrees Celsius case, so if you don't tweak the operating conditions. However, tweaking the operating conditions helps in all cases significantly. Now I want to come to countermeasures against static power attacks, and we have evaluated some of them, practically implemented them and evaluated them on the 28 nanometer ASIC. I only took like a couple of examples of our CHES 2021 paper here. So we have the present cipher, which is some ultra lightweight cipher. We have an unprotected core, so just a normal implementation. It's like a 4-bit serial implementation, one S-box, and 16 nibbles stored in parallel in flip-flops. And yeah, it's about 2,500 gate equivalents large. Then we have a shuffled variant, which is quite cheap, so it doesn't have a lot of overhead. And we have a balanced one. In that paper, we introduce a method to perfectly balance the inputs of logic gates. So if the logic gates would really behave according to this table, where I have like one fixed value for each input combination of 0, 0, 0, 1, 1, 0, and so on, then this shouldn't leak at all. But of course, due to process variations and different parts of the chips having different properties, it's not perfectly balanced. We still wanted to try this because it's like an interesting case study. If this helps more or less, it's definitely a very expensive countermeasure. Then we combined all three of those with masking, so threshold implementation, first order threshold implementation. And then we have these 6 cores analyzed in the following. So here I did the same thing. So for 2 inputs, 2 fixed inputs, I just show the distributions that we obtain, the distributions of the static power. And yeah. So on the top left, we start with the unprotected, then we have the shuffled below it, then we have the balanced below it. On the right, we have everything combined with masking as well. And you can see that from top left to top right, the attacks become harder, because I don't know if you see that on the bottom right, it's 5 million traces that are plotted. On the bottom left, it's only 10,000. So the attacks become harder, the distinguishability of the distribution becomes harder. So we definitely gained something. But attacks still work in the end. So here are the data complexities as first absolute values and then per gate equivalents, so that we have like a relation between the security and the price we pay. And in that regard, the masked plus shuffled variant is actually outperforming all the others. On the other hand, you only need like 600,000 traces to break it, which is still not ideal. I mean, 600,000 traces probably takes you, I don't know, less than a day. So 3 million for the most protected one is also not ideal. So I think like the research on countermeasures there definitely has to continue. And one thing that we recently introduced is some information theoretic approach, which is prime field masking. So on the left side, what you see plotted is the mutual information of the Hamming weights of all shares with plotted over the noise. So what you can see is Boolean masking on the left and prime field masking on the right. What you notice is for the x-axis, which shows the noise, for very low noise levels, Boolean masking doesn't give you anything, right? Boolean masking is my share 1 XOR my share 2 gives me my secrets. Prime masking would be my share 1 plus my share 2 modulo a prime gives me my secrets. And the left variant, really, if I have low noise, I don't gain anything by increasing the number of shares. So whenever I have this low noise scenario, I need to pay very much attention. That's what we saw here. So like the masked implementation without any extra noise generation, it's attackable with 23,000 traces, which is not like a high effort for an adversary. On the other hand, if I use prime masking, we can prove that every uncertainty that the adversary has, so if he doesn't know all the information about all the shares already, but has some uncertainty, it can be 1 bit of one of the shares, then you can still get exponential security in the number of shares. Sounds great. The problem is arithmetic prime field masking you cannot apply to most of the ciphers of the symmetric ciphers that we are using. So at the moment we are developing some toy ciphers and some real ciphers too, which can actually leverage this advantage in low noise scenarios. And we have a paper at CHES this year which shows that if I use masking in prime fields, it actually improves the security up to like a factor of 75 for roughly the same price. So, yeah, for these advanced attacks, it's definitely something that's probably worth to explore in the future, if not ready for strong conclusions yet. Now, to conclude, there is a direct relationship between the feature size of my CMOS technology and the vulnerability of implementations that I realize in that technology to static power attacks. Then I have this advantage that I can use the operating conditions to boost the exploitable information almost arbitrarily. We can go beyond 90 degrees Celsius, what we did here, but then your board dies at some point, right? If you do that over an extended period of time, all the components, they break. I mean, the chip doesn't care much. I think these things, you don't get them broken, but the board will definitely give up at some point, and your measurement equipment that is inside the chamber as well. Yeah, due to the low noise levels, you have some problem with Boolean masked implementations, so you either need to move to some more resistant masking scheme, or you need to generate noise somehow with shuffling, for example, in addition to Boolean masking. And yeah, generally, I would say it's just dangerous to leave sensitive intermediates behind in a circuit. If my coprocessor finishes, I probably should reset it immediately instead of waiting for the next use and reset it directly before the next use, so that everything is flushed or swiped out of the implementation so that no attacker can actually use it. Then I only need to make sure that the adversary cannot control the clock signal, and then I should be fine against this type of attack if no more sophisticated means come into play. Yeah, finally, I would just like to say that I think leakage currents should not be neglected anymore when certifying devices, because I'm pretty sure that there are devices out there which are susceptible to this kind of attack, but still pass certification. I haven't found such cases yet, but I also didn't search a lot. I'm pretty sure of that. You can make your own picture. Yeah, that was my presentation. Thank you very much.
Question? Well, thank you for your presentation. I just would like to know the effect of the process variation on the static power.
Yeah, it's significant, and it's also more significant in the smaller feature sizes. But I don't know how to exploit that as an adversary, so I'm not sure it's like a security thing. What we did is looking at aging. Aging is also more affecting the cells in smaller technologies, and aging actually helps you because it decreases the static power overall. But I mean, your device gets slower, less performance, so it's not a good countermeasure.
Have you tried to compare several devices using the same technology and try to find the number of traces that you attacked? For example, yes.
Yeah. I mean, we did that on like a couple of chips because we have like 100 samples of each of them, and the differences are, I would say, like less than a factor of 2 usually.
Okay. 2 is big. Thank you.
Hi, thank you for the nice talk. The 28 nanometer was FDSOI or bulk?
It was bulk CMOS.
So if you use FDSOI, then you are in a better position to control the static leakage.
Yeah. I mean, you have this bump when going first from bulk CMOS to FDSOI or FinFET. where like the leakage currents don't increase at this level. But then if you compare multiple FDSOI technologies, it still increases. I mean, it's not immune to static power. We would wish it would be, but it isn't.
The other question was on the body biasing. Did you explore that, or is there something which you would like to investigate? So controlling the body bias as a means to either alleviate or decrease the effect of the leakage.
You mean if I design cells?
So let's say a certain commercial 28 nanometer or 22 nanometer FDSOI allows for so your body bias voltage to be controlled either in a forward or in a reverse biasing mode. So is this something you think will have a very high impact on the static leakage and hence on the let's say recovery of the secrets?
It may be, but I don't know. So I cannot give you a good answer to that.
Okay. Thank you.
Any other question? Okay.
Hi there. Thanks for the explanation. That was really good. I have a pretty general question about the experimental setup that tends to be used, I've seen in these side channel types of experiments. I'm not terribly familiar with them, but I noticed that there's always a special board that has two halves, and you explained this. And the power is completely isolated from one half to the other. One half is used, I think, as a part of your measurement apparatus, and the other half is your test specimen. Maybe could you elaborate a little bit more on the exactly what is happening on each of those two halves, and whether, I mean, maybe you wouldn't be able to get such a clean isolation. Maybe this is an important question, but would it be more difficult to attack a real-world device in the absence of that type of measurement setup?
Yeah, I guess no. This is just to have like clean conclusions for scientific purposes. This is not what you would do in like a real-world device, in like a real PCB for these types of chips, I guess. Because I mean, there's less incentive for that. For us, it's just important that we cannot influence with the power consumption of the FPGA that we use to control the chip, that we cannot influence the measurements that we take of the chip. Because if we have that, we might get wrong conclusions. For example, if I do t-test results, I didn't show any, but if I do like TVLA and just check if I can distinguish two classes, then my board usually does the decision whether like a fixed or a random or a fixed group is computed, and this has a different power footprint. So after millions of traces, you tend to see that on the measurements of the ASIC if you don't have this isolation. So it's mostly for getting clean results to get like the right conclusions. It's not really an issue for the susceptibility of the device itself.
Very good. Thank you.
I see in your presentation that you used only correlation power analysis. You think that if you move to template attacks, you may find another difference? Or
yes. I mean, so these things, these are CPA. It's very slow, sorry. Okay. These are actually moments correlating DPA, which is a side channel collision attack, where you use part of the traces to model and part of the traces to attack. It's very similar to a template attack if you don't have profiling access to the device. So you do not do profiling in advance. You separate your traces, and then you use one part essentially for profiling without knowing the key, and the other part for the attack. So that's kind of leakage model independent. We have also used template attacks, and of course, the more your leakage model deviates from like a simple bit model or Hemingway model, the more it helps. So, template attacks are definitely usually the better solution to argue about the security of the implementation. That's, you have this present implementation. It has like the S boxes, and usually it does them from 1 to 16. And this one just has a randomized order of the S boxes. So only every 16 times your same S box is actually processed in the same cycle that you expect. And we assume that the adversary cannot predict the randomness that is used to shuffle.
Okay. Any final questions? Okay.
Yeah, sorry, I didn't really have time to go into detail. Masking is basically secret sharing. So you take your value that you want to protect and you split it into a number of shares so that only like the XOR or the combination, usually an additive combination of those shares, gives you the secret, which helps you against side channel attacks because then the side channel adversary has to find information on all of those shares, then combine it to learn about the secret. And that's how masking essentially works. The thing is that you have with Boolean masking is if you know like 1 bit of all shares, it already gives you 1 bit of the secret. For this prime field masking that I mentioned at the end, 1 bit of all shares gives you some information, but it doesn't give you 1 bit of the secret. It gives you less.
Okay, thank you.